Right, well, welcome everyone. I'm here to give you a little update on a project that we've been working on for the past year on developing a low-cost, high-accuracy building ventilation screening tool. So the motivation for this project is that our project partner of Naval Facilities Northwest needs a fast and accurate ventilation verification tool to improve indoor air quality. For those of you who aren't familiar with Naval Facilities, they're the organization that are responsible for operating, managing all of the building facilities that the Navy has across the world. Naval Facilities Northwest is located in Washington State, and they're primarily focused on the bases that they have there. If you think about it, a lot of buildings on military facilities have been around for a long time. So as they get updated and repurposed, it provides a whole host of challenges in terms of redesigning the HVAC system and making sure that things are built and updated appropriately. So we're working with them to address this problem that they've identified where as they're doing these projects, they continually have issues where the indoor air quality is not as expected based off of the building design. So currently they have a pretty long process of trying to get the contractor back into the building to reassess it. So we're hoping to help them by developing this tool that they could use in-house. And I didn't actually put on this slide, but the funding for this project is provided by the Office of Naval Research. So to give you a little more background, the current practice is for determining indoor air quality based off of the building design is to do some testing, adjusting, and air balancing. And this is an iterative process where someone goes around to the individual spaces within the building, tests, adjusts various dampers or fan settings, and tries to just balance the total airflow so that the distribution throughout the building is as expected. This type of work is done by a certified contractor or inspector. It's a well tested practice, so there's a standardized methodology. And the overall goal of this is to make sure that the HVAC system is working as expected and that you're getting the amount of ventilation air that you need per design specs. So to give you a more concrete illustration of this, I put together this simplified diagram here where we have a single unitary HVAC system that's serving a single office space. So to balance this, you'd want to go in and make sure that you're getting the amount of airflow that you expect into the space. And then to determine the amount of ventilation air you're getting, you would measure the amount of ventilation air that's going into the unit. So this is pretty simple in this example where you just have one system. But the first thing I want to give you more details on and to think about is how is the airflow commonly measured when we do this in actual systems. So one tool that you can use is called a hot wire anemometer. It uses a small heated wire to measure the air velocity that is passing it. This type of tool requires direct access to the duct. Like you can see in this picture here, you need to actually be able to put the wire into the airflow to get the measurement that you're after. Another way that you can measure the velocity of the air is using a pitot tube. And the pitot tube, which is pictured here, allows you to measure the dynamic and the static pressure within the duct. And then you can use that relationship to determine the velocity as well. So both of these are going for the velocity of the air moving through the duct. You need to be able to get access to the duct. But one potential benefit for the pitot tube is that it can be pre-installed. So you can just go in and plug in some pressure tubing as opposed to having to make a new hole and put the probe into it. So I had mentioned these are both just measuring the air velocity. So to get the actual flow, you need to know the geometry of the duct so that you can convert the velocity into a volume flow. In this process, it can be a little bit challenging. By best practices, when you're taking these measurements, you should be following these log Chebyshev weightings. which is showing you the number of points depending on the spacing of the number of points you want to make for the geometry. So up here we have a 4-point and a 6-point example where it's taking the square duct and you're getting 4 points distributed across the horizontal and the vertical dimension. For the circular duct, we're looking at a 6-point example where it's distributed both in the horizontal and the vertical. And taking these measurements is what's required to get an accurate velocity profile for the duct so that you can then convert that into an accurate volume flow. So if you think about this, if you're trying to just verify the measurement in the simple example that I showed you, it's not just a one and done type scenario. You're having to take some fairly precise measurements, with a handheld tool, and then some post-processing to get the result that you want. Another option for this that can also be used are a flow hood or a powered flow hood. So in these pictures up here on the upper right are examples of flow hoods. It's basically a canvas capture device that you can put over a register that you see in a space, and it directs all of the airflow down to the actual base of the tool where the measurement is taken. And these tools themselves are primarily using pitot tubes as well, like I had previously described. It has an array of them, so it's as it's pushing the flow through the sensor, it has a distributed a measurement, spatial measurement that it then uses to convert to volume. So these devices are pretty easy to use. The one pitfall though is that they only work in a relatively small range. So if you are going to a space where you have a wide range of airflows, you'd potentially need multiple sizes just to be able to take those measurements. The final one I wanted to talk about is a powered flow hood, which is probably the least common. And in that case, you're using a flow hood, but you're also using an associated calibrated fan. And the reason for this is that when we put this device over the grill, you're technically changing the back pressure that airflow is seeing, which impacts the flow that is truly coming through that register. So what the powered flow hood does is the powered flow hood allows you to account for that extra pressure that you're adding to get a more accurate measurement. So now that we have a sense of that, let's look at a slightly more complex example where we have a single unitary HVAC system that is serving 2 zones. So similar to the other example, you can definitely use one of the tools that I just described to measure the total flow going into zone 1 and the total flow going into zone 2 and the outside air that's entering the system. But what then happens is, if you notice, there's no way for you to know if this outside air is truly well mixing with the air that's coming back from the space before it returns to the space. So you might get a measurement here that shows 50% of the flow and a measurement here that shows 50% of the flow, but there's no way to know if 50% of the outside air is truly within that volume, and the same for zone 2. So this is kind of the problem that we're truly going after with this low-cost tool that we're trying to develop. So our tool uses the CO2 decay method, which basically just we're measuring CO2 directly in the space as well as outside. And the kind of underlying assumption here is that the outside air was always going to have less carbon dioxide in it than the indoor space. And by watching the carbon dioxide within the space decay towards the outside air concentration, you're able to figure out what the air change rate is in that volume. So we really like this approach because if you think back to the previous example there, you are, by measuring CO2, you are directly measuring the outside air that is entering the space. So there's no need to make a assumption of that it's well mixing within the ducting system and that the ventilation air is actually going where you want. To make it easier to use, we're developing it to have wireless sensors to simplify the test setup time. So instead of having to go to each room and measure each grill, you could put a sensor in each individual room and then be in a centralized location, have them all connected, and then watch the data stream. So all of this sounds really good. There still are a couple negatives to this. One, it does require you to have the room volume if you are wanting the actual ventilation measurement, because what we truly measure is the air change rate. So to convert that to the ventilation rate for the room, we do need the volume. And then currently, we test when the space is unoccupied because one of the underlying assumptions we make is that there is no CO2 generation in the space. That once we're testing, it's only decaying, and the source of the decay is the outside air. So what you can see here on the right is just an overview picture of our system. The gray box is one of our sensors. I'll give you a few more details on that in a couple slides. A CO2 source. So if you were in a space where the CO2 concentration was not already elevated to a high enough point, we would want to add CO2 to the space. And then this is just kind of giving you an example of right now how we're communicating to the sensors with the computer and a rough sense of what some of the decays kind of look like. So here's our sensor. We've gone through a couple prototypes at this point throughout this project, and where we've landed here is what you see in this prototype on the right. It's a combination of an absolute pressure sensor, our CO2 sensor, a lower antenna, and a power supply. The reason for the absolute pressure sensor is to make the CO2 sensor more accurate. The lower antenna is how we're doing our wireless communication. And if you're not familiar with that type of antenna, it also allows you to build a mesh network within the sensors themselves. So if one sensor isn't able to communicate directly to the main hub, it's able to use its whatever sensor is close by to pass its message. Currently, we are powering these devices just through USB ports, primarily either on a computer or a wall board with an extension. But the whole goal right now is eventually we'll move to a power supply, so these could be battery operated and would not need to be plugged in individually. So we've been testing these for about 6-ish months now. We've done testing inside of our laboratory, and we've tested within the Eco office on the UCD campus. The next steps in the project will be doing some more testing on campus and then actually testing within some naval facilities. So I wanted to switch to the results for now. So here's a simple result that we saw in our laboratory testing. So in this laboratory testing, we have a very well-controlled environment where we're able to control the ventilation rate very accurately. And we also have a bunch of other instrumentation to measure the air properties. So we're able to make sure that the air is well mixed. And what you can see here is for this test where we were running at basically 3¼ air changes per hour. It took about 4 minutes of monitoring with our CO2 sensors and our analysis method to converge to the actual air change rate that we expected. So that's a really exciting result in the sense that it takes a relatively short amount of time. One of the things that we're getting at, and I kind of alluded to with those other measurement methods, is that they can be relatively labor intensive, having to carry this tool around the whole building, take it up and down a ladder, potentially to get to the ceiling. So being able to do something like this where you can kind of place sensors in the space and then monitor data for a period of time has the potential to truly reduce that cost there, which is exciting. So even with all these great results that we saw in the lab, some of our field results are a little more challenging to interpret. So we were doing testing at the Eco Office on the UCD campus. And if you're not familiar with that building, it has some individual office spaces as well as some open workspace. You can see in this diagram, these are the individual offices. And then, there's kind of some big open areas for work that are used as workspaces as well. We use this building initially because it has a dedicated outdoor air system that is providing the ventilation air. And that system also has a energy recovery heat exchanger in it. So it's as it's pushing air into the space, it's also pulling air and recovering some of that energy to either heat or cool the outside air. So since this was a pretty simple ventilation system, it was a good candidate for us to start testing with. So as you can see, for space the 3 here, which is the conference room, when we measured this with the flow hood through the supply duct, we were measuring 43 CFM, and through the return we had 52. So you're getting some unbalanced flow there. For space 4, we measured 60 CFM in the supply and 0 in the return. For this office up here, we were measuring 0 in the supply and 20 in the return. And then for this space down here, we had 23 in the supply and 36 in the return. So what you can start to see is if you're using a flow hood, you're going to you would have gotten a different answer if you were just measuring the supply or the return grills. So then when we ran our decays, and you can see those results on the green part of this table here, you see numbers that do not really correspond with either of the numbers that were captured by the flow hood. So what's kind of going on here, and we're continuing to investigate this, is the decay method is kind of giving us, since the decay method is measuring the actual outside air that's going into the space, with this open floor plan, it's very possible that some of that air is not actually coming through the supply. So since you have these unbalanced flows here, some of these spaces are actually negatively pressurized, so they could be having flow from other spots within the building. And since all the airflow that is flowing through these ducts is the ventilation air, that's how you can be getting some big numbers. So it was good to see that we can take, a quick measurement to verify that all of these spaces were being ventilated, and in some cases potentially over-ventilated. And one of our next steps is to investigate a little bit further, just to confirm that these larger numbers are in fact due to flow coming from other spaces, and not an issue in our methodology. So another result that I'd wanted to share that we're working through currently, you can see in these 2 charts here. So in this upper chart, this is actually from a different test that we ran because we have 10 sensors instead of 5. You can see that as we are going from the pre-test part to adding CO2 here to then going to measure our ventilation rate, there's a range of concentration measurements here. And it's actually a lot bigger than we expected. So we were kind of operating under the assumption that as we added CO2 to the space and allowed it some time to mix, you would mix really well within the space. But as you can see here, before we added some, basically a fan to truly mix the air better, it was possible to measure both 2,000 and 1,000 parts per million within the same space. So this finding can make our method a little challenging, but it's also showing us that it's, it's still possible, but very important to make sure that the room is well mixed. One other potential thing that we can do with this is if we're now going to, recommend that there's multiple sensors within the same space, we then have the option to potentially prompt the user to let them know that they're not getting good mixing by having, a wide range of values within the same space. So we're about halfway through this project. What we have coming up next is we're going to continue to iterate on our design. And the reason behind this is we're still trying to address that very specific problem statement regarding naval facilities Northwest. So as we build this tool, we kind of let them interact with it, get their feedback, and then we continue to iterate. So at this point, we've gone through a couple iterations in terms of the hardware, and right now we're working on the user interface with them to make sure that it's easy to use in a format that they would be comfortable using. We're going to continue testing on the UCD campus. I had mentioned we'll go back to the eco office when we have at least one other building lined up to test. And then we're currently in the process of identifying which buildings on the naval base we will go to this summer, which buildings we'll use for those demonstrations. So that's the end of what I have today. So I will open it up to questions.
Thanks, Caton. All right, so if you have questions, please raise your hand or put your question in the chat and we'll get, here we go. Oh, no, we're just getting someone else attending they're late, they missed your presentation. All right. I had a quick question, Caton, how much CO2 is needed, like to do some of the demonstrations you did? Like, is it a lot of CO2 or you need multiple canisters, or how much is needed to test the space?
So, I mean, it is going to depend on the volume of the space, but it is relatively small because in some sense, we kind of were looking to get to a concentration of about 1,500 to 2,000 ppm. And as I had mentioned, outdoor is around 400. And like if you went into an office space that was properly ventilated, but was previously occupied, it might be somewhere between 800 and 1,000. But we're still talking about parts per million here. So, with a pound of CO2 or a couple of pounds of CO2, you can raise that concentration pretty significantly. So one of those canisters that I showed will have currently lasted us, multiple tests in different buildings.
Let's see, we have a question here from Claire. If a home is stuffy, would one assume that it is a high CO2 concentration? Possibly.
That, is kind of probably one of the ways that these complaints come in. And they're definitely complaints that, like NAVFAC gets in terms of comfort, like, this building's stuffy. But it's not the only possibility. So, we use CO2 kind of as a proxy for some of the other contaminants that could be in air, the assumption being that if you have a high concentration of CO2, you have a concentration of those other things as well. So in some cases, yes, if you feel like it's stuffy and wet, that's an indication that you would want to take a quick measurement and get a sense if you're getting the proper amount of ventilation air.
Great. Other questions? You kind of alluded, Caton, to how it's, it's supposed to be, it's a low cost and easier kind of method than the standard methods. I mean, do you have an estimate of, like, I know you're probably working on that for the next iteration, but like the cost, is it like a twofold savings, or, it's how drastic is the cost savings potentially, and kind of human powered need to test?
Yeah, so the human powered, we don't have a good answer for yet because we're still working through that methodology. But in terms of our actual sensor, each one, we're essentially using off-the-shelf parts. So without economies of scale, you're looking at like less than $75 to buy the individual parts. So, you still have to think about if someone was going to build a true business around this, there would be additional costs there, but kind of what I'd showed in terms of those flow hoods are in the thousands of dollars. Powered flow hoods are even more than that. The anemometers and pitot tubes are, less than that, but still in the hundreds. So, I think we're pretty close to where we want to be. In terms of this, there's still kind of that question of, what would the end price be if you were truly going to make this a business where you were selling these sensors.
Great. Okay, well, thank you, Caton, for giving us an update on this project. And I put oh wait, we have another question. Can you see Caton, Claire's question, our follow-up question in the chat, or I'm happy to read it if it's easier that way too.
I got it. Let me read it.
Okay.
So Claire, maybe clarify a little bit more. I'm confused on if you're trying to keep the windows closed to keep allergens out, or if you're not operating the heat pump fan because you're primarily trying to save energy. Yeah, it's okay. She clarified. Yeah, so dealing with allergies can kind of be a struggle, especially within residential spaces, because for the most part, your residential system is just recirculating the air within the space, and is potentially dependent on infiltration from outside for the ventilation. But if you do have a dedicated ventilation system, then you're obviously getting ventilation air through there. So, it kind of becomes a balance of, if it's stuffy, there's definitely the benefit between letting some of that fresh outside air in to dilute the concentration of some of those indoor pollutants. But there's additional complications with that because the filters within your space, if you're truly trying to get rid of some of those allergens, are going to do better by not letting in more air and just continually recirculating it.
Yes, I certainly can relate to allergies this time of year and the balance, challenges and balance required. All right, well, with that, I will let's turn it over. We'll thank Caton and we'll turn it over to Shamim for his presentation. Thank you, Caton.
Thank you.
Okay, good afternoon, everyone. Just let me share my screen. Okay. Just 1 second, I have to switch the screen. Okay, is it good to see the PowerPoint view?
Yeah, it looks great.
Okay, thank you again for inviting me to present my research interest. And this presentation will be a little bit different. It's not a kind of targeting kind of a specific research. It's kind of a blending from of what I did and what could be my research interest and some of my future idea what I will do for the indoor farming. So basically, I will talk based on the aspect of energy barrier for achieving the goal of sustainability in indoor farming. Before starting the main talk, I would like to give some idea like why do we need the indoor farming? So the effect of the climate change that have some significant effect in terms of the climate change for different sectors. So the agriculture is one of the major sector is kind of significantly impacting because of climate change. And that kind of causing the frequent drought. And also we are getting some extreme climates. And also we have some also the flooding problem. So these all are kind of the impact that we have in the agricultural sector because of climate change. And that kind of forcing us to think about the alternative system for growing crops in the indoor space. And also beside that, things like our agricultural practice have kind of the trilemma problem. So what is the trilemma means? Like first we have our traditional practice causing significant environmental impact, like degradation of our soil quality, and also at the same time, the food production from a particular zone could need to be transported, and that causing significant food mileage. And also we are kind of using our natural resources significantly, and that causing significant problem for our environment. And this is very well-known statistic that we are expecting almost 1.7 billion additional people by 2050. And we have to produce 70% more food by the time to ensure the food security for the world population. But by the time we already using our 80% of the arable lands. And also at the same time, the other statistics is showing that by 2050, almost 70% of the population will be moved to the urban area. So that will cause a significant impact for the agricultural practice in remote area. So this kind of giving some idea of why we need the indoor farmings. Definitely the indoor farming will not be the ultimate solution, but that will be kind of one of the aspects to kind of ensure the food security for the in-case world population. So for indoor farming could be in the different form, could be the traditional, the conventional style greenhouse using the sunlight, could be some kind of the vertical farm in the warehouse or kind of some facilities like inside the building, could be some smaller scale, the household level production, could be the multi-stored plant factories. And also sometimes it could be the small, like the container shape facilities for growing the plants. Now let's give some idea a little bit about the market trends, like what is the current global market for the indoor farming. So based on these statistics, we can see that the expansion of the indoor farming is quite high compared to the open field production because of that impact that we have and also losing our arable land. So among different form of the indoor farming, so the vertical farming is one of the most interesting things that is kind of expanding a lot. So based on these statistics compared to 2013, we can see by 2023, we are expecting almost 16 times expansion of this industry. So that is kind of giving some idea like why this industry is kind of having more importance and what is the challenges. So in terms of the challenges, as today's presentation is mostly based on the energy aspect. So the energy is one of the biggest challenges for this industry. Also, we have some limited technological support for the indoor industry, and there have the limited number of crop cultivars that could be grown in the indoor space. Still, people have some wrong perception about the quality of the product that grown in indoor. And also there is not enough strong business model that could be kind of applied to analyze the profitability of this industry. So now let's talk about the energy problem for these indoor growing facilities. So this is very well-known statistics that the food supply chain is one of the major contributor for the greenhouse gas emission that could be the up to 30% of the total emission. So this is one of my research that is kind of showing that how much the energy could be contributing. So this research was conducted in Canada during my PhD study period. So we are trying to analyze like if some greenhouse is constructed in northern Canada, very cold region. So what will be the heating requirement for growing the common vegetables that is required for the peoples. So you can see the heating energy consumption is quite significantly high per square meters. And based on our economic analysis, we can see that the heating cost is the second largest operational cost for growing crops in cold region like northern Saskatchewan. And that is kind of need to be addressed, like how we can kind of minimize that cost to see that industry as a kind of sustainable. So this is for the traditional greenhouse. Now look at about the vertical farming or completely closed farming facilities inside the building. So in that case, even the energy cost is even higher than the labor cost. That means the maximum cost is kind of contributing from the energy sector. So if we would like to see like what is the different component of that energy, we can see the lighting is the major portion of that energy used, and the remaining part is mostly used for the HVAC system like heating, ventilation, and the air conditioning. And all other component is kind of just contributing about 1% of the energy. So that is kind of giving some idea, like if we really would like to see that industry is sustainable, we have to reduce the energy cost by up to 50%. And also at the same time, we have to kind of reduce some operational cost up to 30% for making this industry as sustainable for growing foods in the indoor space. Now, I would like to talk about some idea, like before, like I just mentioned the different two scenario of the indoor farming, the greenhouse and the plant factory. So this graph is kind of showing some common idea, like for these two types of facilities and how the energy component is contributing. So it was conducted for 3 different locations, the UAE and the Netherlands and the cold region in Switzerland. So you can see like for the indoor farming, like basically the plant factories facilities, the most of the energy is contributing for the lighting and cooling and the dehumidification. But for the greenhouse, it's mostly required the heating and a small portion for the cooling. And another interesting things you can see in terms of the energy load for the plant factory, even it's higher if in the greenhouse, if they consider the free energy as a solar energy into their calculation. So that means like, although this industry like the vertical farming is expanding, but the major challenge is the energy, especially for the heating, cooling, and the dehumidification. So based on that aspect, like I will give some more idea about these 3 different components of the energy use in the indoor farming. First, later talk about the heating. So the heating is a major concern in the cold region. So I will present some of my results, like what could be the possible things that could be done for reducing the heating cost for the indoor growing facilities. So based on my previous research, like as the research was conducted in cold region in northern Saskatchewan. So first we try to see like what could be the different shape that we can optimize or kind of make a design that could be more efficient in terms of the energy use. So based on the transient simulation analysis, first we can see that we consider the different parameters that could be more significant, like, you know, shape, orientation, angle, and the span. But for today, like mostly I will kind of briefly present the result for the shape and the orientation. So in terms of the 5 of these different shape, we can see first we did the analysis in terms of the solar gain, because that is one of the major contributing factor to the indoor space, especially for the greenhouse. So you can see the uneven span shape receiving the maximum solar heat gain because of the longest surface exposed to the outside to receive the solar radiation. But if we analyze in terms of the heating requirement, we can see that this effect is not anymore balanced in terms of the heating. And in that case, like you can see, like even the uneven span, the even span although receives the lowest solar heat gain, but in terms of the heating cost, it's kind of almost same to the uneven span. And like the other shape, like the binary and quinset, also it's just a very small solar gain, but in terms of the heating efficiency, it's more efficient because This is cold region. In that case, the heat loss is significantly higher than the heat gain for the surface exposed to the outside. Now, in terms of the orientation, we just try to kind of analyze based on the solar heat gain. So you can see the east-west orientation is more efficient in terms of the heating during the cold period and also the cooling for the summertime. This is for the single spin greenhouse. Then we try to also analyze like what will be the impact in terms of the multi-spin greenhouse. Now we can see still there have some significant benefit in terms of the heating and also like much better benefit in terms of the cooling, but it's not that much impact like the single spin. Again, this is kind of depend on the ratio of the surface area exposed to receive the solar radiation and also the indoor growing space. So in that case, this ratio is significantly low. So that's why this impact is minimal here. So the another things could be like the solution for the energy aspect, like especially for the heating problem for the cold region. So we try to kind of adopt some Chinese style solar greenhouse that is kind of very popular in China for growing winter vegetables in northern regions to kind of maximizing the solar energy and storing that energy on the north wall and kind of release that energy at the night time, so that way they can kind of minimize the energy requirement from the secondary sources. And also they're using some sort of blanket that kind of could be covered in the nighttime to reduce the heat loss. So based on our analysis, we found that these kind of growing facilities could reduce almost 50% of the heating cost compared to the conventional style greenhouse in the same location. But definitely this is kind of could be more efficient in terms of the energy, but there have some problems in terms of the growing space efficiently used inside the space. Then we also try to do some kind of analysis, doing some sensitivity analysis, like what kind of parameter is more more dominant to understand the heating cost. So we consider the different large number of parameters, but for today we'll kind of show like the impact of the thermal conductance of the airspace between two layers of the cover, and also the thermal conductivity of the blanket, and also the insulation along the parameters. So these three parameters in terms of the design is more dominant to reduce the heating cost for this kind of greenhouse in cold region. So now I will talk about some of my research in terms of the cooling, because that is kind of the common scenario for the growing space in California or similar kind of climates. So based on my previous research when I worked in the City University of Hong Kong, so we try to kind of evaluate the absorption cooling system based on the waste heat from the different sources. So this research mainly focused to use the waste heat from the vapor compression cycle to run the absorption cooling system, especially for the process of the desorption. And similar kind of technology also could be used, like using the waste heat from the other sources, and also could be the solar based the energy harvesting, and that could be used also to run the absorption cooling system. So based on the vapor compression integration with the absorption cooling, based on our analysis, like we can see that using the silica gel and water as a kind of the working pair, the efficiency, like especially the cooling capacity and the COP, could be significantly improved, and that could be provide some additional benefit to cooling the space, indoor space. And also this kind of facilities based on the waste heat from other sources could be used for the low grade the cooling purpose, like greenhouse or others like warehouse type facilities. This efficiency definitely could be improved with the use of high grade heat, like the high grade heat for the regeneration of the silica gel, and that starting it to be kind of complete other how much we can achieve using these kind of facilities for indoor growing space. So another solution for the cooling facilities for the indoor space could be the evaporating cooling. So this is very common, like they use the direct evaporating cooling for the indoor growing space, but that could be very efficient solution for the greenhouse like structure. But mostly like high-tech plant factories facilities, this kind of facilities, they don't allow to enter the outside air to maintain the hygiene of the plant growing facilities. And also at the same time, the direct evaporating cooling could be a big concern for the high humidity. And the humidity is one of the major concern for indoor growing, especially the fully closed facilities. And also the Legionella bacteria is one of the major concern for this kind of the direct evaporating cooling system. So in that aspect, like based on my working experience in the industry, so I work on different types of the indirect evaporating cooling system that is used for the data center applications. So based on that understanding, like I think the indirect evaporating cooling could be one of the solution for the indoor growing space to kind of minimize the impact of the dehumidification, also at the same time avoid the infiltration of the outdoor air to the indoor space for the ventilation purpose and for the humidity control. And also at the same time, like this technology could be kind of avoid to use the traditional, like the mechanical based cooling for the indoor space. Now I will talk quickly about the dehumidification. That is another component of the high energy used for the greenhouse. As I mentioned, like when the plant do the transpiration, and that kind of causing the significant water condensation in the indoor space, and that caused significant problem for the plant health, especially cause different types of disease. So from that aspect, it's very important for the farmers or even the industry to kind of maintain the humidity. So the very common scenario, like, or also I would like to mention one thing, the difference between the plants and the human control. So in case of the human, like the comfort zone is kind of very small range, like the temperature 22 to 24 degrees Celsius. But for the plants, like every plant is different and their comfort zone is also different. So in that case, like we cannot kind of provide some kind of unique solution for the growing space, because depending on the indoor plants, this dehumidification methods and the efficiency could be different. So the common techniques for the dehumidification used currently is kind of use the outdoor air kind of for ventilating and expel the humid air from the growing space. But based on these studies, you can see that like for the cold region, this is one of the major problem, and the dehumidification cost is significantly high. Like per hectare, it could be 22,000 Canadian dollars only for the dehumidification. So based on that, so like we just try to kind of evaluate the different types of the dehumidification system, like the mechanical dehumidifier and also the desiccant-based dehumidifier and heat recovery ventilation system, and also the traditional outdoor ventilation system. So you can see that the mechanical dehumidifier and the desiccant-based dehumidification system is kind of more efficient in terms of maintaining the temperature and the humidity level. But still, like this kind of mechanical dehumidification system is definitely like we try to avoid that things to really achieve the goal of the sustainability. And also the desiccant-based dehumidification system is the major problem. This kind of releasing the heat to the indoor space, and that kind of increase the cooling load for the plant factories. So based on that, like when I work in industries, like we try to kind of design a patent kind of the liquid desiccant-based dehumidification system, and is also kind of using two different heat exchanger, and that kind of separating using a kind of the membrane. So this way kind of we can minimize the air exchange with the outdoor air. So we can provide the hot and the dry air to the indoor greenhouse space. And there could be this regeneration could be using the solar-based operation, or also kind of some other sources, like the small heater could be used for the regeneration of the liquid desiccant. But still, again, this problem like in the hot region. So like this hot air could be significantly add the cooling load to the greenhouse. So in that case, like still like the dehumidification is one of the major concern for indoor growing space. What could be the efficient techniques that could be applied for most regions, and depending on the season also. So this device like that, when I work in the industry, like we can see that this is relatively efficient in terms of the cost for the cold region. So compared to the mechanical dehumidifier or the others, direct contact desiccant dehumidifier system. Okay, now I will just quickly finish some of my research plan or the research need that need to kind of investigate to see the sustainability of this industry to reduce the energy cost for the heating, cooling, and the dehumidification. So the first, definitely we have to focus the concept of the net zero for agricultural built environment. So in order to do that, like we need to analyze more, especially for the plant factories, like how we can kind of minimize the energy use, especially through design the building envelope with the control system, and also the use the renewable energy based operation of the HVAC system. And also another things we have to focus like how we can kind of making this system as a closed system so that we can use the rainwater for the irrigation purpose, and also we can kind of convert the biomass that is growing in the indoor space for the energy production. So this way you can kind of make this production system more sustainable, but still we have to do lots of research to kind of see that system as a kind of the sustainable based on the concept of net zero. So another things like I'd like to quickly say that as the plant factory is kind of becoming a high rise and also big industry, so the HVAC system become kind of more complex. So based on my previous research, like we can see in the building sector, it has a kind of the major problem in terms of the fault detection and the diagnosis. So ongoing commissioning could reduce a significant amount of the energy for the HVAC system. So the similar things also could be adopted for the agricultural building like the plant factory, so that we can kind of minimize the energy cost, and that need to be kind of done some analysis, doing some research in the agricultural building. Another important aspect, the lighting that I previously showed that this is one of the major component for the energy use for the indoor farming. And every plant, they have kind of the different requirement in terms of the spectrum of the lighting. And the different lighting also have the different kind of function for the plant growing aspect. So in that aspect, like currently kind of 3 different types of the lighting system is using, like the high pressure sodium lightings, and also some kind of the LED lighting, and sometimes like combination of these 2 for the indoor growing space. But it's still like there have some research gap, like how we can kind of making this lighting system more efficient. So I would like to share one of the case study conducted by the Department of Energy from the USA. So you can see that in terms of the lighting for the agricultural growing facilities, it's improved significantly in terms of the photon flux efficiency, but still we are kind of quite far to achieve our target that could be required for the agricultural production. And also they showed another things, like if they kind of replace all of the high pressure sodium light or high density lighting system with the LED, they can reduce like 34% of the energy savings. But this is just kind of the concept in terms of the replacement of the LED with the high pressure sodium, but all plants might not do the same response with LED. So that's why we need some more research, like how the LED could be more efficient for other types of crops besides the leafy greens. And finally, like agricultural system is kind of very complex in terms of the combination of the different discipline. It's kind of combination of the plant science, the engineering, data scientist, economist, and also the different discipline of engineering. So in that case, definitely there's the energy is one of the major component for these growing facilities. And in that case, definitely like the different discipline from the engineering could be kind of contribute to kind of the energy conservation, and also reduce the energy cost for these production facilities. That's kind of everything in a short, lots of things as a kind of within short time. I'd be happy to answer any question if you have, and thank you again.
Thanks so much, Shamim.